This screencast is going to provide an overview of degree of freedom analysis. So we'll provide an explanation of what this means and how it can be used to help us analyze engineering problems. So when we're doing a degree of freedom analysis, we're basically trying to find out whether we have enough or too much information to solve a particular problem. So before we look at an engineering example of doing a degree of freedom analysis, we can kind of get an intuitive sense of what degree of freedom analysis means by looking at a couple systems of algebraic expressions. So we'll look at three scenarios. In the first, we have one equation. We have 2x plus y is equal to 7. And if we were asked to solve this, we intuitively know that we can't because we only have one equation with two unknowns. So we could rearrange this however we want to solve for x or y, but we'll never be able to solve for both of these variables. So in this case, when we have the number of unknowns is greater than the number of equations, we have an underspecified system. We can't solve for the two variables in this equation without more information. In other words, another equation. That's not the case in our second scenario, where we have two unknowns, x and y again, and two equations. In this case, the number of unknowns is equal to the number of equations. And this is generally the scenario that we're looking to find when we're analyzing engineering problems. In this case, when the unknowns are equal to the number of equations, we have 0 degrees of freedom, and we can solve the system of equations. In this case, if we solve these two equations simultaneously, we would find that x is equal to 2 and y is equal to 3. And in our third scenario, we still have our two unknowns of x and y, but here we have 3 equations. So we have a different scenario where the number of unknowns is actually less than the number of equations. And in this case, we are overspecified. If we have an overspecified system, we can get results or answers for our unknowns that are inconsistent. So for example, if we use the first two equations to solve for x and y as we previously did, we show that x is equal to 2 and y is equal to 3. If we use the second two equations, we would get a different answer for x and y. So here x is equal to 0.5 and y is equal to 3.5. So we have a system of equations that aren't consistent with each other and aren't generating a single unique solution. So when we're analyzing engineering problems, we're trying to find a system that has 0 degrees of freedom and provides enough information so that we can solve for the unknowns for a particular problem. If we're trying to solve an engineering problem and we're interested in analyzing or modeling chemical process, doing a degree of freedom analysis is going to be one of the first things we want to do. And we can calculate the degrees of freedom by calculating the number of unknowns for a particular system and subtracting the number of independent balances that we can write, whether it's mass or energy, and then also subtracting the other equations that we can write that relate those equations. I'm going to focus on the material balance side of this, and if we want to look at the number of independent balances we can write, it's always going to be equal to the number of species that are present in that particular system. We can always write an independent balance for each species that's present. We can also write a total balance, but the total balance is not independent from the species balance. In other words, if we sum up all the species balances that are present, that will generate the overall balance. So it's dependent on all of the species balances. The other equations can come from a variety of different places. So for example, we might have process specifications. So we might know the relationship or the ratio between different flow rates in a particular part of the problem. We also could have physical property data. So for example, we might know the density or specific gravity of a liquid stream, or we might know the pressure and temperature of a gas stream, which would allow us to use the ideal gas law to figure out a flow rate. Could also use equilibrium equations. So there's a lot of different other equations that are different than mass balances that will allow us to relate unknowns, and we can account for those as well. When we calculate the degrees of freedom for a particular system, there's 3 potential outcomes. If we have a situation where the degrees of freedom are equal to 0, then we can solve the problem. We have the necessary equations to relate the unknowns that we have. On the other hand, if we have degrees of freedom that's greater than 0, we have more unknowns than we have equations, and we have an underspecified system. So without more information, we can't solve for all of the unknowns. And if we have degrees of freedom that's less than 0, we're overspecified. In other words, we have more equations than we do unknowns, similar to what was shown earlier. So let's apply this procedure to 2 different examples of material balances on single units. In the first example, we have a single unit process with 2 inputs and 2 outputs. If we want to calculate the degrees of freedom, we need to know the number of unknowns as well as the number of balances that we can write. If we take a look at our flow chart here, we can see that we have one unknown flow rate here on the input side. We also have another unknown composition variable on the output side and one more unknown flow rate. So with M1, X, and M2, we have 3 unknowns. If we want to solve for these 3 unknowns, we can write out a system of mass balances, and the number of independent balances is always equal to the number of species. So we have species A, we have species B, and we have species C. So in this case, there are 3 independent material balances that we can write. And again, keep in mind that we can also write the total, but the total will always be equal to the sum of the 3 species balances. So therefore, it is not independent from the other 3. We don't have any other information that's been given to us that can relate the variables in this particular example. So with 3 unknowns and 3 balances that we can write, we have 0 degrees of freedom, and we could solve for the 3 unknowns in this case. All right, let's look at one more example of a single unit with 1 input and 2 outputs. Again, if we want to do the degrees of freedom analysis, we need to know the number of unknowns. So in this case, we have 2 unknown composition variables on the input side. We have an unknown flow rate on the output side, as well as another unknown composition variable, and one more unknown flow rate. So it looks like we have a total of 5 unknowns in this particular case. The number of independent material balances is always limited to the number of species that we have. And like the first example, we have 3. We have A, we have B, and we have C. So with only 3 balances that we can write and 5 unknowns, we would have 2 degrees of freedom and we would have an underspecified system. However, we have some more information that we can use. On the right here, we see that we have an equation that relates 2 of the flow rates. Here we have M3 is equal to 0.1 times M1. So that's not material balance per se, it is an equation that relates 2 variables that's independent from all the balances that we would write. So we have -1 other equation for this particular ratio. That leaves us with 1 degree of freedom left. If we look at the input side, we can show one more relationship that relates these variables. So we know that the sum of all the mass fractions has to equal 1. So we have one more variable on the flowchart than we really need. We could equivalently write y is equal to 1 minus 0.2, which is a mole fraction of A, minus x, which is the mole fraction of B. So often it's advantageous to write the composition variables on the flowchart with as few variables as possible. That's actually what was done here in the second flow rate. So if we keep this constraint in mind that all the mole fractions sum up to 1, then we have another equation that we can write, as we just did, and that leaves us with 0 degrees of freedom in this case as well. So we could solve for all 5 variables in this example as well. So hopefully this shows that through these 2 examples, the degree of freedom analysis is a really powerful tool to quickly help us determine whether we have enough information to solve a problem. It's straightforward on a simple unit. It becomes even more important as we look at more complex processes with multiple units. So it's often a good place to start with degrees of freedom analysis for the different systems in a particular problem.